Hi everyone. Today I'm going to present about a project. Myself is Dario G. Our project title is Image to Biomass Prediction. Okay. Our agenda is introduction, statement of the problem, scope of the project, methodology. Methodology we are going to discuss about the five different components, then how to present test cases, conclusion, future work, and references. Okay. In introduction part, we are going to discuss about the biomass estimation, that is the raw part of this project. That is, the biomass estimation is critical component of agriculture monitoring, so which helps to predict the crop health, productivity, and ecosystem sustainability. So, the accurate estimation of biomass also helps us to make a precision agriculture, yield forecasting, and resource management also. So, the conventional biomass estimation methods rely on manual field sampling, which is a labor-intensive, time-consuming, and often destructive, making them impractical for large-scale or continuous monitoring. So, through the RGB imagery, we are going to feed it into a model which is going to detect the biomass values, which is the regression value, through the imagery part. Okay. Statement of the problem is the accurate biomass estimation helps to effective agriculture monitoring, yield assessment, and sustainable resource management. However, existing biomass estimation methods predominantly rely on manual features measurement, which are time consuming, labor intensive, destructive, and unsustainable for large scale or frequent analysis. Although recent advances in computer vision and deep learning enables biomass estimation using RGB images, achieving reliable prediction remains challenging. Okay, the scope of the project is the project focuses on developing a deep learning framework. Yes, exactly. We are going to develop a deep learning framework which is going to estimate the multiple evocative biomass components using the high resolution RGB images. Okay. Utilizing these images by the transformer based models, the system aims to accurately predict the five different categories, that is dry green, dry dead, dry clover, grain dead matters, and dry total biomasses. The proposed system can support precision agriculture by providing accurate biomass information that helps farmers monitor crop growth and vegetation health. Okay, and this also help them to manage the irrigation, fertilization, and harvesting strategies also. Okay. Let us discuss the methodologies here we are used. So first of all, we are going to discuss about the data preparation, data collection, and model development. Through data preparation and data collection, actually we are collecting data from the Kaggle data set, which is provided by the CSIRO, which is Australian-based company. They have provided the 357 RGB images. In parallel to that, they also provided the CSV file. In CSV file, they mentioned the RGB images also. That is the image path of every images. So there we have get the data set. So first of all, we are preparing the data set by splitting the data set into 80 into 20 ratio. That is training data set is 80% and 20% is the validation data set. So our data set is used by the models to predict the dry green, dry dead, dry clover, GDM, and dry total biomasses. Okay, so our model here we are used is DynoV2 model, which is a self-supervised vision transformer model. This DynoV2 model is used only for the backbone. Actually, we are going to predict the five regression values. So DynoV2 is used in the used for the image classification, image reduction. So for its valuable thing in the image extraction, there is feature extraction. We are going to use it in the backbone. But after that, in the backbone, that is in the front part, we are going to use the multi-head self-attention mechanism. So it uses the future extract from the data video and helps to predict the five regression values. Okay. So then, for explainability and validation metrics, we have used RMS, that is root mean square, R square is a coefficient determinant, and MA, which is a mean absolute error. So in our previous diagram, we are going to discuss about the architecture of my project. That is a flowchart of my project, which is first of all we are going to give the input image, that is RGB image, then image pre-processing. We have used the resizing, normalization, data accommodation, RGB extraction. Then feature engineering. In feature engineering, we have used EXG, that is extra green, EXR, which is extra red, then sober. So there we have passed it into the six channel image formation, that is RGB, EXG, or sober. Then we are going to use the DynoV2 after that multi-head self-protection mechanism. Okay, so the use case diagram where we have used is pre-processing image split into dual views, extra DynoV2 used with attention, predict multiple output biomass visualization results. Okay. Then the sequence diagram, we are going to use the dataset, upload image, preprocessor, load image, splitter, resize and normalize, DynoV2, creates left and right views, attention, feature extraction, regression, fuse, features, output, is prediction by mouse. in design class diagram also, the data set loader, which is image processor, then dual viewer generator, dyno v2 feature extractor, attention fused models, then regression head, classification head, loss function, training edges, physical post processing, evaluation metrics. Okay, then in algorithm we have used generative model, right? So which is the proposed biomass estimation system follows a structural deep learning pipeline designed to predict multiple epochal biomass components from RGB images. Initially, the data set containing image path and the biomass labels, which is loaded for the training series values. And both views, that is left and right views, are passed into the dynamic diffusion transformer backbone, which extracts high-level semantic feature embedding using self-supervised representation learning. Okay. So the hardware here we have used is the processor. Sorry, the processor, which is Intel Core i5. Hard disk is 250 GB, RAM is 60 GB minimum. GPU is NVIDIA. So the implementation details are given here. Actually, we have used the PyTorch, which is a deep learning framework. Then we have used the dynamic diffusion transformer. Then also we have used the self-supervised, this multi-head self-attention mechanism. So this is the code we have imported. That is this is the training.py code, and this is the prepare.data code. In conclusion, we are going to discuss the project represents the advanced deep learning framework for estimation multiple component above frameworks using high resolution organization. In the futures, we are going to introduce the multispectral imagery, LID or data or canopy height models combining RGB and feature representation of vegetation, which may significantly improve the biomass estimation accuracy